right, so now we're going to continue with the remainder of our hypothesis tests, and these will be focusing on two sample tests. We covered one sample tests in Chapter 9, and we will cover the two sample tests now. There are two primary ones we will concern ourselves with. These will be ones for comparing two proportions, and then for comparing two samples. We'll start off with our proportions. In this case, when we're comparing two proportions, what we care the most about is, did they come from the same population? If they didn't, they came from different populations, and therefore, one of them is going to be greater than or less than the other. Now, if they came from different populations but had the same mean, then it probably wouldn't fail the test. So on this basis, because two-tailed tests are more restrictive than one-tailed tests, and we are most interested in whether or not it's reasonable to assume that they came from the same populations, our tests for hypotheses involving the difference between two proportions is almost always going to be two-tailed. So in this case, we will almost always have our null hypothesis as P1 is equal to P2, i.e. there's no reason to suspect that they're different, coming from different populations. And our alternative hypothesis will be that P1 is not equal to P2. You can rewrite these as saying P1 minus P2 is equal to 0, and P1 minus P2 is not equal to 0, or the other way around. This one's the easiest way to write it, and the most intuitive. Now, because it is two-tailed, our p-value is always going to be equal to double of the probability of being below the z-score, i.e. on the lower end. So if we get that probability in the lower end, we have to double it because we have two tails. In a similar vein, when we're getting our critical values, we're going to be looking for the z-score corresponding to alpha over 2 of the data points being below that critical value, again because we're on both tails. Now, when we're getting this test statistic, once we have it, we'll just call it a ZT. The remainder of the work is the same like it was in Chapter 9 with a one-sample proportion for two-tailed. We get the p-value the same way once we have that test statistic, and we get the critical value the same way once we have that test statistic. The primary difference is in the computation for the test statistic itself. In order to get that computation, we need to get what we call a pooled estimator. Put another way, let's suppose, because that's what the null hypothesis is supposing, that these two proportions came from the same population. Then it would stand to reason that if we took these two samples and put them together, that should estimate the population. And so this is what we call our p-bar, the pooled estimator. This is equal to the weighted average of the two proportions. So it'll be the sample size of our first proportion times that proportion, added to the sample size of the second proportion times that proportion, divided by the total sample size of both samples. If both of them are going to be the same sample size, then it'll be equal, so it'll be the halfway point. If one is twice as large as the other one, then it'll be twice as close. Once we have this pooled estimator, i.e. what we could estimate for the population as a whole, then we can now get our test statistic. The numerator is going to be the difference between the two proportions. In this case, because we're testing equal to not equal to, and our formula takes the negative of the absolute value, which one that you denote as your first sample and your second sample does not make a difference because the signs will cancel out either way. In our denominator, we have an alternate form of the square root rule, which I'll explain in a moment. But this part right here, p-bar times 1 minus p-bar, that's our variance, so that's familiar. Where the square root rule comes in is here. If you want to break up, you can think of it as we square root this, and we also are square rooting that. That's just a product rule for radicals back from high school algebra. In this case, you might ask, why are we adding the reciprocals of these two? I get why they're in these denominators of these fractions, but why are we adding the reciprocals and not doing, say, 1 over n1 plus n2? The reason why is because we recall the rule for sample size, and that is that the margin of error does not decrease linearly with our sample size. It decreases rationally. Polynomial in the denominator. And if we put both of these two in the denominator of the same fraction, that would be a more linear decrease. And so doing this keeps us consistent with the rational rule. So now that we have this, let's go over an example. So here, we're going to use a very real example. Back in the 2020 presidential election, it was expected that Wisconsin was going to be a close state, and most of the polls were suggesting Biden had a mild lead, and the ABC News and Washington Post came out with a poll that said Biden had 57% of the vote. That would correspond to winning the state by 14 points. That doesn't pass the smell test, but what we're going to do is use what we've learned in our stats class to show why the poll has to be junk. So I'll give you a moment to solve it. If you need time, you can go ahead and pause right here to work it out. All right. So we have to start with our hypotheses. In this case, our null hypothesis is that the proportion from the first pole is equal to that of the second pole. And our alternative hypothesis is that they are not equal to each other. Now, since we have a 95% confidence level, and alpha plus the confidence level has to equal 100%, our alpha is 5%, which is 0.05. Now, we can proceed to doing our computations. We first need to get our pooled estimator. Since each of them has the same sample size of 1,000, it's going to be the halfway point, but let's show using the full formula. In this case, we're going to have a sample size of 1,000 times 51% for our first pole. We'll have another sample size of 1,000 times 57% corresponding to our second pole. And then we divide this by the two sample sizes added together. And this comes out to 54%. Now that we have that, we can get our test statistic, so I'll call that ZT. And this is going to be equal to the difference to the two portions. And again, in this case, we can do the negative or the positive. Doesn't matter because we're going to take the negative of the absolute value anyway, so we can deal with the complement law. So we'll just take our first one as 51%, and our second one is 57%. And now we divide it by the square root of the pooled proportion, which is 0.54, and then times 1 minus 0.54. And then finally, this is multiplied by the sum of the reciprocals of our sample sizes. And this, if we round it to 3 decimal places, is going to be about negative 2.692. Now, we need to get the probability associated with this test statistic. In this case, we're going to take negative 2.69. So we first look for the negative 2.6. That's right here. We then look for the 0.09, which is right here. Because of the 2, it's basically going to be on the 9, and WebWorks increased tolerances will mean that even if you say round it up for some reason, the negative 2.7, the slightly increased tolerances mean you shouldn't run into rounding issues. So if you're getting it wrong, you know it shouldn't be due to rounding. So in this case, this will have a corresponding p-value of 0.0036. But that is the probability of being below this. So p, z is less than zt is equal to 0.0036, But since it's a two-tailed test, we have to double this because we have that same area in both tails. So therefore, our p-value is given by 2 times pz is less than zt. So that is this. So 0.0072. Because our p-value is below our value of alpha, we will reject the null hypothesis that these two poles are the same, i.e., they're different. So, because our p-value of 0.0072 subsedes the level of significance of 0.05, we reject the null hypothesis that the two poles essentially came from the same population. In practical terms, at least one of these poles must be wrong. They both could very well be wrong. Now, as a practical matter, in the 2020 election, the first poll is actually right. But what this test tells us is that at least one of these polls has to be bunk. It's got to be useless. And our understanding of how Wisconsin works, it being a very closely contested battleground state, means that the 57% makes no sense and is not a poll you should put into your weighted average. It just makes no sense. So, this next one's going to be more conceptual one, because I want to expose you to both ends of it. So here, we're now going to move to Nevada. We got two pollsters doing polls of Nevada in 2020. Each has much larger sample sizes of 4,000. One has Biden at 51%, the other has him at 49%. So I'm asking you 3 concept questions. So if you want to work these out, you can go ahead and take a moment, you can pause, and then we will go over the correct answers. All right, we'll start with our first one, and I'm going to change our text to red to indicate our answers. So for our first one, we ask ourselves, why do poll numbers near 50% make it difficult to reject a null hypothesis of the two polls having originated from the same population? And here's why. Here, I'm going to mark this as A. The culprit is the standard deviation, and here's why. No matter what the difference between the two polls is, let's suppose that P1 minus P2 is equal to some difference delta. We don't know what it is. Let's just call it something. Whether or not they have similar sample sizes isn't going to matter. And so let's suppose that the P bar, that our pooled sample variance corresponds to P1 and P2. You don't have to write this down, it's just notation. This means that this P bar is the pooled variance corresponding to P1 and P2. In this case, what the sample sizes are doesn't really matter here. And here's why. We recall that our test statistic is equal to this difference, which we've called delta. This is some constant. Let's just fix it to a constant. Doesn't matter what it is. You'll see why in a moment. Divided by the square root of P bar times 1 minus P bar. And then, from up here, again by radical rule, we can pull out the square root and the reciprocal. So times the square root of 1 over n1 plus 1 over n2. So what we're going to do, we're going to fix our delta, our n1, and n2. Doesn't matter what. You can throw values in it. Doesn't matter. Just fix them to something. What that means is that this delta divided by the square root of 1 over n minus 1 plus 1 over n minus 2 is a constant. This is a constant. We're going to call that c. We can pull out this, because you can say this is 1 times that, so we just split up the fractions. So our z-score is equal to 1 over the square root of p bar times 1 minus p bar times some constant. It does not matter what this constant is. All that matters is that this is a constant. So we're left with this. Let's now look at this p bar. We know that p bar has to be between 0 and 1. You can't have 150%. In fact, if we make a graph, and this is our p bar, and we go from 0 to 1, and we have zt, this could be zt divided by z, so just this, or put another way, our 1 over, let's deal with the square root. So in this case, let's suppose that p bar is 50%. If p bar is 50%, we have 0.5 times 1 minus 0.5, so 0.25. Square root of that is 0.5. If p bar is 0, it's going to be 0 times anything, square root still 0. If it's 1, 1 minus 1 is 0, so we're going to have it down here. Now, let's suppose that p bar is 1/4. Then we have 1/4 times 3/4, so 3/16. And if we square root that, then it will be the square root of 3 over 4. So that's going to be up here. Similar logic holds. Spoiler alert, this is a parabola, and it's going to look like this. What does that mean? Well, if the denominator is largest at 50-50, then our zt will be smallest at 50-50. If our denominator gets further and further away from 50-50, then that makes, well, if our p bar does, then our denominator becomes smaller and smaller, which therefore makes our zt larger. Therefore, and here I will write it out, therefore, all else held equal, pooled proportions closer to 50% result in smaller test statistics and hence make it more difficult to reject the null hypothesis. Now you might look at this and think, this is a ton of algebra. I don't understand what is going on here. Here's the good news for you. You don't have to understand exactly what's going on there to do well in the test. What matters the most is that you understand if you're 50-50, then it's going to be halfway through. It's very much so a theoretical thing. I'm not going to test you on it that heavily. You just need to be familiar with the result. I figured it'd be appropriate to show you where some of the theory comes from. So speaking of which, part B, using the formula for the pooled proportion, show that if the two proportions have equal sample sizes, this pooled proportion has to be halfway between the two. So in this case, for part B, pooled proportion, it's P1 bar plus P2 bar, multiplied together over, well, by their sample size, by the sum of those sample sizes. If they have the same sample size, let's just call it n, because n1 equals n2, just call it n. Then we're going to have n times P1 bar. Well, we have the bars up here. Whether or not you use P1, P2 doesn't matter. I'll move these all to bars for consistency. There we go. Plus n times P2 bar, and this is divided by n plus n. Well, we can factor out all of the n's. So we factor out the n over n. We factor out the n from this. So we have P1 bar plus P2 bar. And our denominator becomes 1 plus 1. The n's cancel out. 1 plus 1 is 2. So P1 bar plus P2 bar over 2. This is why if sample sizes are the same for each sample, it's going to be the halfway point. You get to skip the whole formula and make it much easier on yourself. Finally, for part C, suppose that the magnitude of our test statistic exceeds 5. What will the associated p-value be, and explain your reasoning? Well, if the magnitude of our test statistic exceeds 5, then the absolute value of zt must be greater than 5. Okay, so we're asking ourselves, based on our formula, our p-value is 2 times pz is less than the negative absolute value. So let's take the lowest possible one. What is the value of 2 times p zt is less than negative 5? Because we have negative times the absolute value, so whatever the zt is, absolute value that makes it negative, we'll make it below here. Well, think of it this way. This is nowhere on our table at all. The lowest our table goes is negative 3, which corresponds to 0.0013. That's nearly, well, actually, technically the lowest our table goes, is all the way out here. The lowest that is 0.001, but that's basically negative 3.09. So put another way, here's our normal distribution. That puts us right here. We're asking for negative 5. That's all the way out here. There's nothing there. There's just nothing there. The p-value is going to be basically 0. And the reason why this p-value will be basically 0 is because we're so stupidly far away from the mean proportion, so our proportion, that, well, in this case, standardized, of course, to the normal distribution, so the mean. We're so far away from the mean, it's just not happening by random chance. If this sounds confusing, think of it this way. Suppose that the class average on a test was an 80 and the standard deviation was an 8. If you had a z-score of 5, then you would be 5 standard deviations above the mean. So you would have gotten a score of an 80 plus 5 times 8. That would be 120. No one's getting 120 on a test purely based on their answers to the questions. They had some extra credit or something, or there was a typo or some shenanigans going on. But that is not happening by random chance from the questions alone. So, let's now move on. I will briefly talk about match samples, but the computations do not matter too much for these. And the main reason why is because these can be done entirely by computers without much thought into it. In fact, the computations for these are really nasty. But the good news is, these results these results are tables when you think about it. The other ones, they were like, means and proportions. This one is basically going to be a table. You're given a table of data and asked to do a test on it. In this case, you can literally put the table into Excel and just ask Excel, what's the probability of this happening by random chance? It'll give you that p-value, and from there, it's no different from any other test. But regarding the test itself, match samples are when one person or a group of things takes 2 tests. In this case, what is a test? It could be a literal test like an exam, or it could be a survey, for example. And we're asking ourselves, these 2 tests, are they comparable? If they're comparable, the scores, whatever the scores represent, should not be significantly different. And that's the idea behind matched samples. We take these scores, whatever they represent, and see what are the chances of these differences arising by random chance. So for example, you could take 2 different Unit 3 tests, and I could have all of you do that, so have 100 students take 2 different Unit 3 tests of supposedly different difficulty levels, and I can compare scores across them and test to see, based on matched samples, if that difference could have arisen by random chance. If it couldn't have, then these tests are not exactly comparable. And I use tests in the literal sense there, but it could be a survey, such as evaluations, to compare 2 direct professors if all students are the same, and much else held equal, along with other ones. You'll notice here, the computations get really nasty. The formulas might make it look nicer than it actually is, but in terms of actually doing all the messy math, it's very much so on the level of hypergeometric when it comes to computations. So in this case, we go over it as a concept, but what happens in practice is you have your table of results. Say the table of those 100 students taking those 2 different tests. We put that table into Excel, and we ask Excel, what's the chance of having a random chance? It's just a literal formula from the technically 2 arrays. And then Excel will tell you the p-value. From there, you know exactly what to do. You compare p-value with alpha, like with before. However, let's move to the other one. And this occurs all the time, arguably the most common type of 2-sample test, and it's called the 2-sample t-test. It is essentially the inverse of matched samples, when we have one test takes 2 people. Now, that might make no sense whatsoever. I think that, what? Test can't take you. You take the test. Well, if you're in Soviet Russia, test takes you, but putting the jokes aside, think of it this way. Let's suppose that I take the Unit 4 test and I give it to all the students in the spring, and then of course it's given to all the students in the fall, and I want to see if the students in the spring did better or worse, put another way, they're different than those in the fall. The test is the same, it's the students that are different. So the test takes those students to tell us whether or not there's a significant difference. Now again, we have test in quotation marks because it could be a survey, it could be maybe sales. The point being, whatever we're testing people on stays the same, it's just the people or the entities, could be corporations, are different. Another way of thinking of it is, let's suppose we got a lake and people fish in the lake, and the people on the southern side of the lake are accused by those on the northern side of the lake of overfishing. If they are overfishing, then there should be a significant difference in the fish population on the 2 sides of the lake, again assuming it's sufficiently large. So if there's not overfishing, then the number of fish on each side of the lake, proportionately speaking, should be roughly the same, i.e. the same source. So we're trying to test whether or not it's, for all intents and purposes, the same length. But if people on the southern end are overfishing, they might as well just be 2 different lakes at that point. So here, our degrees of freedom come back. Our degrees of freedom is equal to the sum of the 2 sample sizes minus 2. You might say, why 2? Think of it this way. The degrees of freedom of the first sample is n1 minus 1. The degrees of freedom of the second sample is equal to n2 minus 1. So this is just adding the 2 degrees of freedom together. Now you might be asking, why are we subtracting 1 or 2 here? Remember, back from Unit 1, because these are samples, we have the n minus 1 on denominator for the sample standard deviation. And so that minus 1 repeats itself here. What we then have to do is pool the variances together. You might ask, why? Well, we have to get an estimate for the overall sample standard, the overall population standard deviation, because we don't know what it is. We got to get an estimate for it. Our estimate for the population mean, if these 2 are the same, would be the null hypothesis, that there's no significant difference. Now, we do assume that the population variances are equal with these formulas. There are scant cases where they aren't equal. Those computations would be worse than hypergeometric and matched samples. But here's the nice thing. Using that lake example, suppose that the people on the southern end are overfishing. Oh, does that mean the fish are suddenly going to be having less sex, whatever that means? Are we going to have less fish mating because there's overfishing? Maybe there'll be more, maybe there'll be less. No, there shouldn't be too significant of a difference. Put another way, just because the means might be different, that doesn't mean the population variances are going to be different. And by definition, if the 2 means came from the same population, well then they gotta have the same variances. The only way they're going to be different is if they came from different populations. So here we'll primarily concern ourselves with what occurs more often in nature, because this is very much so an applied course, and I want to show you the uses of this. Now, we technically do have one-tailed test here that does pop up, say, It's lower on the southern side of the lake, but here's why we'll usually use two-tailed. First of all, we're testing whether or not they're different. That's the main thing. If they're different, it's going to tell us which way it is. If there's far less fish on the southern side of that lake, it'll be obvious from the fact that x2 bar is going to be much lower than x1 bar, assuming the null hypothesis is rejected. Additionally, because the p-value for our two-tailed test is doubled, it necessarily means if it fails the two-tailed test, it's going to fail the one-tailed test. And here's why. Let's suppose our cutoff critical value is here. Well, and that's two-tailed. If it's one-tailed, we don't have to worry about this end, so we add that error to the upper end. So that'll be here, for example. Necessarily speaking, that's lower critical value, and therefore, if you're going to reject for two-tailed, you'll reject for one-tailed in this example. So, to get the pooled sample standard deviation, we take the weighted average of the two sample standard deviations. Those are given to us, S1 and S2. We have to square them for variance. We weigh them by the sample size minus 1. Put another way, we're weighing it by the degrees of freedom. You might say, why? Why are we weighing it by the sample? Simple. Again, remember, we have that n-1 correction factor from unit 1. It will repeat itself. This gives us S squared. So finally, our test statistic is equal to the difference between the two means divided by the square root of our variance and then the pooled reciprocal rule for our square root event rule. So let's go over a couple examples. The first one's going to be a bit easier than the second one, computationally speaking. If you're paying attention, you can see why. So here, I'm going to give you a moment for you to work on it and go ahead and pause, and then we will go over the answers. All right, let's start with the value of the standardized test statistic. This is going to be equal to the difference in our means divided by s squared times 1 over minus 1 plus 1 over minus 2. Well, our test statistic is going to be 83.2 minus 83.2 divided by the square root of s squared times 1 over n1 plus 1 over n2. You might ask, hold on, what is s squared 1 over n1 plus 1 over n2? You haven't told us it. Doesn't matter. Why? Because this is 0. If that's 0, no matter what the numerator is, this is going to be equal to 0 over that, which is 0. So our test statistic is literally 0. So now we're going to skip part B and go to part C. If the test statistic is 0, then everything is within it. Everything. If the test statistic is 0, that means there's no difference. So there's a 100% chance that could have happened by random chance. So therefore, this p-value is going to be 1. Put another way, this is our hypothesized mean, and we landed right on the mean. That's the most likely outcome. Everything is within it. So we would have our p-value of 1. Now our rejection region, because it is two-tailed, we know that we're going to have some sort of union involving a negative infinity end and an upper infinity end. In this case, we now need to compute our degrees of freedom. Our pooled degrees of freedom is equal to 41 plus 46 minus 2, so 85. In this case, we have 85 degrees of freedom, but our value of alpha is 0.01. If you choose 0.01, you're going to get it wrong because this is not one-tailed. This is two-tailed because we're looking for a difference in the two classes. Therefore, we take alpha over 2 in the upper tail, so 0.05, because we have to have an equal amount in each tails. These two have to add up to 1%. So therefore, we have 0.005 in the upper tail, which corresponds to critical value of 2.635. So, the absolute value of our critical value is equal to 2.635. Put another way, it's positive and negative 2.635. Finally, do we reject or not reject? Well, no matter what, we never reject or not reject the alternative. It's only the null, so A and B immediately make no sense. Well, our p-value is obviously 1. There does not exist any confidence level where you reject that, so we're not going to reject based on the p-value. Additionally, our critical value of 2.65 gives a rejection region of here, so if we were to reject, our test statistic has to be within here. 0 is obviously not inside this interval, so therefore we will fail to reject the null hypothesis. All right, let's give you one where you actually have to do some computations. For this one, sometimes your p-value doesn't show up in the table, so you need to use an online calculator. Here, I have a link here. In this link, it'll just give you your fields. You put in your test statistic, you put in your degrees of freedom, and you put your confidence level and how many tails you are, and it'll tell you what the p-value is. So, I'll give you a moment. Go ahead and work on it. And if you need time, you can pause. And then we will go over the answers. All right, let's go over the answers. So now we can't use the nice cheap shortcuts we had. Our degrees of freedom will be equal to our 2 sample sizes added together, minus 2. So we have degrees of freedom of 99. Now we need to get our pooled variance. So our S squared is equal to our first sample size of 49 minus 1, so the first degree of freedom, well, the degrees of freedom associated with our first sample, times its variance, which is going to be 16.8 squared, so by the way, S1 squared, and then plus the degrees of freedom for the second sample, so 52 minus 1, times the variance for our second sample, so 18.8 squared, and then we divide this by our total degrees of freedom of 99. And this, you throw it in your calculator, it comes out to be roughly, I believe it was 318. Let me quickly double check. 48 times 16.8 squared plus 52 minus 1 times 18.8 squared over 99. Yes, 318.919. So now, finally, we get our test statistic. So our t is going to be equal to the difference between these two. So 86.3 minus 82.1 divided by the square root of this. So 318.919 times the reciprocal of our 2 sample sizes added together. And this will come out to be roughly 1.181. So our test statistic is 1.181. Our rejection region, if you use the bounds we had up here, you'd be wrong because our degrees of freedom have changed. We have degrees of freedom of 99. Again, since it's a 2-tailed test, we have to have equal areas in the upper and lower tails. So 0.01 over 2, 0.005. So our area, the critical value, the absolute value of the critical value is equal to 2.626. Therefore, our rejection region will be from negative infinity to negative 2.626, and then 2.626 to infinity. Finally, our p-value, I've saved us the time and gotten it straight from using this website. We input our t-score, our test statistic of 1.181. We have 99 degrees of freedom, and our confidence level is 1%. That doesn't change the p-value, although 1-tailed or 2-tailed does. Remember, our truth table is doubled it, but this will do the math for you. Our p-value, round to 3 decimal places, is 2.40. I'm sorry, 0.240. In this case, because our p-value does not subsede the level of significance, we will fail to reject the null hypothesis. Again, H1 makes no sense here. We're going to fail to reject. Additionally, our critical value does not lie inside the rejection region, so no matter what, we will not be rejecting the null hypothesis. With that, that's all that we have for Chapter 10 and hypothesis tests. When it comes to the test itself, here's what would happen. If I asked you a question like this, you can get this from math, and you can get this from computations. When it comes to the p-value, it'll either be in a table or it'll be 0. Dealing with these questions, it'd be more like this part. The second one, very much so concept questions, so you could understand where these come from. The test itself, I know I've asked you many concept questions before. The test is very much so going to be about as applied of a test as you're ever going to see in a math class. And if you want to get a much better idea for that, you look at the practice test number 4. It'll give you a very good idea for how the test goes. So with that, hope you have a great rest of your day.